Today in this class we are going to study what are electrochemical cells and how do they work, what is the significance of salt bridge, and how do we find single electrode potential with respect to standard hydrogen electrode. So, electrochemical cells. What are electrochemical cells? In any electrochemical cell, chemical energy involved in the reaction converts into electrical energy. The chemical energy involved in a redox change, that is nothing but free energy change. This free energy change involved in the redox reaction, that is called chemical energy, that converts into electrical energy. Electrical energy here means electrical work done, and this electrical work done is expressed in terms of EMF of the cell. The total relation comes out as delta G is equal to minus NF into EMF of the cell. So, this is charge transferred during the redox change as well as potential difference between the two electrodes. The product of these two is nothing but electrical work done, and this electrical work done is equivalent to change in free energy of the redox reaction. Change in free energy of the redox reaction converts into electrical work done. This is numerical relationship. Let us come to know what is an electrochemical cell, its construction, working. Let us say a zinc metal is placed in a solution of zinc sulphate. So, this is zinc rod, this is zinc sulphate solution. Now, here this zinc carries no charge, being metal it is 0, whereas another zinc which is in solution is in +2 oxidation state. So, same zinc but carrying two different charges. This makes one feel jealous about the other. So, this zinc want to convert into zinc +2, whereas this zinc +2 want to convert into zinc. This charge difference between the two zincs make them to change one into the other, and that reaction we can write as zinc will convert into zinc +2, means zinc is dissolving into the electrolyte, or zinc is undergoing dissolution into zinc +2 by the loss of 2 electrons, and this dissolution is oxidation from 0 to +2. So, this is oxidation reaction. And next, zinc +2 from solution take up 2 electrons and deposit as zinc. So, this is the reverse reaction that is possible. So, this is reduction of zinc +2. So, altogether both the reactions occur simultaneously with the exchange of electrons. Zinc loses electrons, goes into solution. Zinc +2 catch the electrons and deposit as zinc. This reversible reaction will reach to the state of equilibrium. At the state of equilibrium, there is certain negative charge developed on the zinc electrode. Certain negative charge is developed on the zinc electrode, and that is decided by the ability of the zinc go into solution as zinc +2 and 2 electrons. So, this reversible reaction develops some potential here, and what is the absolute value of this? One cannot find. So, absolute electrode potential we can't find. Similarly, here copper undergoes dissolution into copper +2, and copper +2 deposits as copper. So, here also we can see two reactions. Copper +2 plus 2 electrons gives rise to copper, and copper gives rise to copper +2 and 2 electrons. Dissolution, deposition simultaneously occurring in this electrode, and that is with the loss and gain of electrons. Once the reactions reach to the state of equilibrium, there is some potential developed here, some negative charge developed here, and this is single electrode potential. The exact single electrode potential here is how much we do not know, and here is how much we do not know, but we can find the difference in electrode potential by connecting the two electrodes with a wire. So, if you connect them through potentiometer, we can see the potential difference, that is observed to be 1.1 volts. When you take zinc plus 2 concentration 1 molar, copper plus 2 concentration 1 molar, so altogether the potential difference is 1.1 volts. So, here before connecting the two electrodes, there is a dynamic equilibrium between these two. Here also there is a dynamic equilibrium between copper dissolution and deposition of copper plus 2, both are there. But the moment you connect, the equilibrium is lost. Only oxidation occurs here and only reduction occurs here. Only reduction occurs here. Reason, this is developing more negative charge density is developed at zinc electrode. More negative charge density is developed at zinc electrode. Less negative charge density is developed at copper electrode. So, here we have developed less negative charge density. As a result of this more negative charge density, electrons will travel from zinc electrode to copper electrode. Means electrons are lost by zinc electrode, zinc passes into solution, delivers the electrons, and the electrons will reach here. If the electrons reach here, they are received by the copper plus 2 to deposit as copper. So, here only oxidation occurs, reduction is prevented, and here only reduction occurs and oxidation is prevented, only reduction. The electrode where reduction occurs is called cathode, and the electrode where oxidation occurs is called anode. So, we say zinc electrode is anode, copper electrode is cathode. And as electrons are driven from zinc electrode to copper electrode, this electrode is conventionally given a sign negative, and this electrode is given conventionally a sign positive. So, anode is negatively charged, cathode is positively charged, which is reverse to that of electrolytic cell. In electrolytic cell, anode is positive, cathode is negative, but here anode is negative, cathode is given positive sign. This is a sign convention, but at anode it is always oxidation, at cathode it is always reduction. The overall cell reaction here is zinc becoming zinc plus 2 and copper plus 2 is becoming copper. Copper plus 2 is becoming copper. This is the overall cell reaction of this electrochemical cell, which is called Daniell cell or galvanic cell, we can say. Now, if oxidation of zinc occurs continuously, the concentration of zinc plus 2 keep increasing. As the concentration of zinc plus 2 increases, the tendency of zinc to go into solution gradually decreases. Means the potential developed here gradually decreases. Similarly, as copper plus 2 keep undergoing reduction, the copper plus 2 concentration here keep decreasing. As a result, the reduction potential also decreases. So, after some time, the ease of oxidation of zinc becomes very tough, as well as the reduction of copper plus 2 copper also becomes very tough due to lesser availability. And due to more zinc plus 2 produced in solution, the solution turns positively charged. The accumulation of positive charges prevent oxidation of zinc. Zinc entry into solution will become tough. It is opposed by the existing zinc plus 2. So, oxidation will become tough here. Similarly, as copper plus 2 is undergoing reduction, plenty of copper plus 2 have got deposited if, then sulfate ions are alone. So, these sulfate ions develop negative charge in the electrolyte. That negative charged sulfate ions will not permit the electrons to enter. So, one side exit of electrons become tough due to accumulation of positive charges, and on the other side entry of electrons also become tough due to accumulation of negative ions. So, this accumulation of negative ions, positive ions in anode, negative ions in cathode, all together will stop. Here accumulation of positive charges, and in cathode half cell accumulation of negative charges prevent escape of electrons, prevent entry of electrons. So, after some functioning of the cell, the flow of electrons is stopped, means cell stop working, it cannot do any more work. So, this accumulation of charges should be prevented in both the half cells. So, in the anode half cell accumulation of zinc charges, zinc plus 2 should be prevented. In the cathode half cell accumulation of negatively charged sulfate ions should be prevented, and for that purpose we need a salt bridge. Salt bridge is what? So, it is nothing but a U-shaped glass vessel, and in that glass vessel we fill agar-agar gel or gelatin, anything we can use, along with either KCl or KNO3 or NH4NO3, any of these electrolytes, one of these electrolytes and one of these glue-like materials. We fix them in a solution, and a saturated solution we prepare. So, in excess of water we will add excess of KCl or KNO3 or NH4NO3 along with some agar-agar or gelatin. So, that solution, hot concentrated solution, is filled in this U tube or U-shaped tube and then kept aside for some time for solidification. After solidification, here we have agar-agar fixed up in the form of solid, and there is KCl or KNO3 or NH4NO3 electrolyte is here in saturated condition. What is the function of this salt bridge? How it prevent accumulation of charges? Let us see. When zinc undergoes oxidation, you will get an extra zinc plus 2 delivered into the solution. This extra zinc plus 2 is responsible for accumulation of positive charges. So, if the positive charge of this is neutralized, discharged by any negative ion, then there won't be any accumulation of positive charges. For that purpose, from this salt bridge, we can say 2 Cl minus ions are delivered. The 2 chloride ions will take care of the zinc plus 2 charge. So, the zinc plus 2 charge is nullified. One more zinc plus 2 is delivered due to oxidation, 2 more chlorides will enter. So, like that, as much zinc passes into solution, accordingly we get too many chloride ions delivered into electrolyte from salt bridge and will prevent accumulation of positive charges. So, this prevention of accumulation of positive charges will facilitate a continuous oxidation. So, there is a continuous flow of electrons from anode. On the other hand, if a copper plus 2 is deposited, its counter sulfate ion bears negative charge, and that negative charge is not balanced because its counter copper plus 2 is deposited. For that charge balancing, from salt bridge we can say K plus ions are delivered into the cathode half cell, into this electrolyte. K plus ions are delivered from salt bridge. So, these K plus ions will nullify the charge of these sulfate ions. The negative charge is being nullified by K plus. So, as many coppers deposit, all their corresponding sulfate ions will find K plus ions delivered into the electrolyte, and therefore, negative charge accumulation is also prevented because enough K plus ions are being delivered into this half cell. So, neither accumulation of positive charges in anode half cell nor accumulation of negative charges in cathode half cell facilitate comfortable oxidation here as well as convenient reduction here. So, there is a continuous flow of electrons from anode to cathode. That is the advantage of using KCl. KCl does not allow the electrolyte solutions to mix. This zinc sulphate solution cannot mix up with this copper sulphate solution, or this copper sulphate solution cannot mix up with the zinc sulphate solution. So, does not allow solutions to mix, but will allow ions to migrate from place to place. So, this is the functioning of the salt bridge which is necessary for an extended working of the electrochemical cell. So, now let us know what is a standard hydrogen electrode or normal hydrogen electrode, which is a primary reference electrode with respect to which we find electrode potential of every single electrode. So, this is standard hydrogen electrode construction. This is U-shaped bell jar and having an inlet for hydrogen gas which is sent at 1 atmosphere pressure, and here we have a solution of H plus which is having 1 molar concentration. So, hydrogen gas is under 1 atmosphere pressure driven and H plus ions concentration is 1 molar. As I said, here also again there is a charge difference. Hydrogen is 0 in oxidation state and hydrogen here is plus 1 in oxidation state. Charge difference is there, phase difference is also there. This is gas phase, this is in solution phase. Same hydrogen in 2 different phases will compete with each other, like hydrogen want to convert into H plus and H plus want to convert into hydrogen. In this competition, both hydrogen will convert into H plus by losing 2 electrons, and the 2 H plus ions from solution will take the 2 electrons and will convert into hydrogen. So, this is the reversible reaction that occurs here, means H2 converts into H plus and H plus converts into H2, that is through exchange of electrons. So, there develops some negative charge density over this platinum plate. So, on the platform of platinum, hydrogen comes and oxidizes as H plus, and the electrons delivered there on the surface are received by the H plus ions and will liberate as hydrogen gas. At equilibrium condition, some potential is developed here. This potential which is developed at standard hydrogen electrode is taken as 0. Taken as 0. Actually speaking, it is not 0, it is something. But for convenience sake, being a reference element, we take this electrode potential as 0, and with respect to standard hydrogen electrode, now we will find electrode potentials of different electrodes like zinc electrode, copper electrode, chlorine electrode, like that different electrodes potentials we can measure with reference to standard hydrogen electrode, which is a primary reference electrode. Now, let us learn how to calculate the single electrode potential of any electrode like zinc electrode, copper electrode, chlorine electrode, etc., with respect to standard hydrogen electrode. So, now here zinc is kept in zinc plus 2 solution. So, there develops a charge difference or phase difference, because of which some negative charge density is developed at the zinc electrode. Similarly, standard hydrogen electrode also develops some negative charge density, and we have taken that as 0. As a reference, we took it as 0. Now, when you connect zinc electrode to standard hydrogen electrode, it is observed that electrons are flowing from zinc electrode to hydrogen electrode. Means that this zinc electrode is undergoing oxidation, means it is acting as anode, and the hydrogen electrode is undergoing reduction. So, it is said to be acting as cathode in this electrochemical cell. So, the electrons are flowing in this direction, means the reaction occurring at zinc electrode is zinc becomes zinc plus 2 electrons, and here the 2 electrons are received by 2 H plus ions and will convert into H2, that is hydrogen gas is liberated here. So, this is overall cell reaction. If you combine these two, you will get overall cell reaction, zinc plus 2 electrons, and the other side 2H plus 2 electrons gives rise to hydrogen, cancelling the 2 electrons, as many delivered those many received. So, we get zinc and 2H plus gives rise to Zn plus 2 plus hydrogen. So, this is the overall cell reaction of this cell. Now, here whatever is the EMF we see, suppose the EMF I have seen as 0.77 volts. 0.77 volts of EMF I have seen, we took it as 0 already. So, the difference is 0.77 volts, higher potential is developed here, higher negative charge density. So, as zinc electrode is undergoing oxidation, this EMF of the cell is taken as oxidation potential of zinc electrode, which is plus 0.77, and therefore, the reduction potential of the same zinc electrode is taken as minus 0.77. What does it mean? If any electrode when connected to standard hydrogen electrode, if undergoes oxidation, its oxidation potential will be positive and its corresponding reduction potential will be negative. Sign only will differ, magnitude will remain the same. So, here zinc is undergoing oxidation, so its oxidation potential is positive, therefore, its reduction potential is negative. Similarly, when you connect standard hydrogen electrode and copper electrode, here also some charge density is developed, that is negative charge density. Here also some negative charge density developed, and we have conventionally taken this as 0. We know it is taken as 0 and we do not know how much it is developed there. But when you connect standard hydrogen electrode and copper electrode through a potentiometer, the EMF of the cell is observed to be 0.34 volts. So, 0.34 volts difference in potential is developed, means with respect to hydrogen electrode, copper electrode has developed a lesser potential of 0.34. This is already 0 and this is lesser than 0 by 0.34 volts. So, this will be minus 0.34 volts. So, what do we say now? This is copper plus 2 is undergoing reduction here because electrons are flowing in this direction. So, here oxidation is occurring. So, wherever oxidation occurs, we call it as anode. Here electrons are received, so reduction is occurring. So, we call it as cathode. So, when standard hydrogen is connected to copper electrode, 𝗧𝗎 act as anode, copper electrode act as cathode. So, corresponding reactions, oxidation at standard hydrogen electrode. Oxidation means what? Hydrogen should become H plus 2 electrons. What is reduction? Reduction means copper plus 2 taking 2 electrons and becomes copper. Overall cell reaction of this cell is H2 plus Cu plus 2 gives rise to Cu and 2H plus, Cu and 2H plus. So, this is the reversible cell reaction. So, EMF of the cell is 0.34, which we call it as, this copper electrode is undergoing reduction. So, the reduction potential of this copper electrode is plus 0.34 plus 0.34, and the oxidation potential of that copper electrode is minus 0.34 volts. So, finally, we can say any electrode when connected to 𝗧𝗎, if undergoes oxidation, its oxidation potential is positive. Any electrode when connected to 𝗧𝗎, if undergoes reduction, so its reduction potential is positive. And let us see the case of non-metal electrode. So, this electrode when connected to 𝗧𝗎, we can see that this is 0, standard hydrogen electrode potential is 0, and the chlorine electrode potential, reduction potential is positive. How can we say? Let us suppose this is 0.75 volts. What is the meaning? The potential developed at chlorine electrode is 0.75 volts lesser than the potential developed at standard hydrogen electrode. That is why electrons go from hydrogen electrode to chlorine electrode. So, which is ready to undergo reduction? Chlorine electrode is ready to undergo reduction. So, hydrogen electrode is ready to undergo oxidation. So, here 𝗧he act as anode and undergoes oxidation. Oxidation means H2 gives rise to 2H plus 2 electrons, and here chlorine electrode acting as cathode. So, it is undergoing reduction. Reduction means what? Is chlorine becoming chloride or chloride becoming chlorine? So, reduction means 0 should become minus, means chlorine gas is undergoing reduction by taking 2 electrons will become 2Cl minus. So, chlorine is becoming chloride ion, that is reduction. So, overall cell reaction is H2 plus Cl2 gives rise to 2H plus 2Cl minus ions. This is the overall cell reaction. And here chlorine electrode is undergoing reduction. So, this EMF of this cell is called the reduction potential of chlorine electrode, which is nothing but plus, say example 0.75 volts, just like that 0.75 volts. So, oxidation potential will be minus 0.75 volts. Like that, we can assign reference electrode potential values with respect to 𝗧he. So, now we learnt how to assign electrode potential for any electrode which is undergoing oxidation with respect to cathode or with respect to standard hydrogen electrode, or which is undergoing reduction with respect to standard hydrogen electrode. So, some electrodes will have positive oxidation potential or negative reduction potential. Some electrodes will have negative reduction potentials or positive oxidation potentials, vice versa. So, if you list them out, now this is called electrochemical series, means each and every electrode one by one connected to 𝗧he, and it is seen that if the electrode undergoes oxidation, its oxidation potential is assigned positive, means its reduction potential is negative. For example, if you take lithium electrode, lithium in lithium plus, when that electrode is connected to standard hydrogen electrode, now the reduction potential, standard reduction potential of lithium is negative, means this lithium electrode undergo oxidation when connected to 𝗧he, means it is acting like anode, means it undergo oxidation. Lithium goes into solution and delivers the electrons, and the electrons are received by standard hydrogen electrode. So, the EMF of this cell will be positive, EMF is positive because this is taken as 0, and this is here electrons are received by hydrogen electrode, it undergoes reduction. So, it is said to be acting as cathode. So, any electrode whose reduction potential is negative, they all are said to have positive oxidation potentials. Reduction potentials are negative, but oxidation potentials are positive. Oxidation potential positive means all of them when connected one by one with 𝗧he act as anodes. So, all these electrodes will act as anodes against standard hydrogen electrode versus standard hydrogen electrode, all of them act as anode. Similarly, if you see some electrodes here, they have positive values of reduction potentials, positive values. So, positive reduction potentials means when each and every electrode one by one when connected to 𝗧he, they undergo reduction, that is why their reduction potentials are given positive. For example, if you take copper electrode connected to 𝗧he, then 𝗧he is acting as anode and undergoes oxidation. Copper electrode undergoes reduction, so it acts as cathode. So, EMF of this cell will also be positive. The potential difference between these two electrodes is positive. So, electrons are going from standard hydrogen electrode to copper electrode. So, here oxidation, you know what is the oxidation reaction? H2 becomes 2H plus 2 electrons, and here copper plus 2 takes up the 2 electrons and undergo reduction to copper. So, all these electrodes when connected to 𝗧𝗦𝗔, they undergo reduction, so they act as cathodes. So, all these electrodes are acting as cathodes against 𝗧𝗦𝗔 with respect to standard hydrogen electrode. So, you may be asked whether a cell reaction is spontaneous or not, or whether a cell reaction occurs or not. For example, we write like this: zinc plus sulfuric acid. We can easily write ZnSO4 plus H2. This reaction is easy to write. Whereas, if you write Cu plus H2SO4, we write HCuSO4 and H2, but this reaction is rather non-spontaneous. This cannot occur under normal conditions. Reason is what? Here zinc is undergoing oxidation. See here, zinc is undergoing oxidation, and simultaneously here H plus ions are there. So, 2 H plus ions are undergoing reduction to H2. So, this reaction, does it occur or not, means whether against 𝗧𝗦𝗔 zinc act as anode or not. If zinc act as anode, it undergoes oxidation. If it undergoes oxidation, its oxidation potential should be positive or reduction potential should be negative. And we know zinc reduction potential is a negative value, some negative value. So, this reaction is possible. Zinc can displace H plus ions from any acid as H2. Similarly, if you write a reaction here, Cu plus 2H plus gives rise to Cu plus 2 plus H2. This is what the reaction in the second reaction. Here H plus is undergoing reduction, so should act like cathode. Copper is undergoing oxidation, so should act like anode. But against standard hydrogen electrode, copper cannot act as anode because copper electrode potential, that is reduction potential, is more than that of the hydrogen. So, copper C2 undergo reduction better than hydrogen. So, copper better to undergo reduction, it has higher reduction potential than hydrogen. So, this forward reaction is not spontaneous, rather backward reaction is spontaneous. Means H2 when passed through copper plus 2 solution, it can give rise to copper and H plus. So, this reaction is spontaneous. In this direction, the reaction is spontaneous, whereas this reaction is non-spontaneous. That is decided by respective electrode potentials. How the application of electrochemical series can be done? Suppose this is electrochemical series we know, and I am taking 5 electrodes here. Let us say E1, E2, E3, E4, E5, and their SRP values are given like this. Now, my first question is, how many of them or which of them will act as anode against 𝗧𝗦𝗔? Out of these 5 electrodes, which will act as anode against standard hydrogen electrode? So, to act as anode against standard hydrogen electrode, the reduction potential should be negative, and these two have negative reduction potentials, means they act as anode versus 𝗧𝗦𝗔, that is E1 and E2, and which will act as cathode against 𝗧𝗦𝗔. To act as cathode against 𝗧𝗦𝗔, they should have positive reduction potentials. So, this is positive reduction potentials. So, which will have positive reduction potentials? E3, E4 and E5. So, all these E3, E4 and E5 will act as cathodes against SHE. Now question is, suppose if any two electrodes are combined, you will get a cell, electrochemical cell. Let us say I have connected E1 and E5. So out of E1 and E5, which has great tendency to act as anode? So the topmost one has the greatest ability to act as anode because its reduction potential is very less, means its oxidation potential is very high. So it is acting as anode, and the bottommost will have the great capability to act as cathode, means out of all of them, E2 has highest ability to act as anode because its reduction potential is minus, more negative. So this is anode. So E2, when you connect with E1, when you connect with E3 or with E4 or with E5, this has the ability to act as only anode. And out of all these 5, the highest positive reduction potential is for E3. So this electrode has the highest capacity to act as cathode. So when you connect E3, E4, E3 will act as cathode, E3, E5, E3 only will act as cathode. With any electrode, E3 has the ability to act as cathode. Now suppose if you select E1, E2 and E3, then what is their ability to act as? E2 has greater ability to act as anode and E3 has the greater ability to act as cathode. So such two electrodes, when you connect, then there will be a greater EMF produced between the two half cells. The EMF produced here we can calculate as EMF of the cell is equal to E of cathode minus E of anode. Cathode EMF, that is electrode potential, is plus 1.8 and anode EMF is minus 1.6. So the sum of these two is plus 1.8 plus 1.6, altogether 3.4 volts. So this much of EMF can be generated between E2 and E3. Maximum EMF is possible between these two. Similarly, in contrary, we can say minimum EMF is between what? Minimum EMF between what means E4 you see, E4, that is plus 0.4. So arrange them according to electrochemical series. Now if you look at these electrode potential values, let us arrange them according to electrochemical series. The most electronegative or most negative reduction potential will be at the top of the electrochemical series, that is E2. Next comes E1, that is minus 1.2. Next comes 0.4, that is E4. Next E5, next E3. So as these two electrodes differ greatly in their anodic and cathodic behavior, connecting E2 and E3 just like these two electrodes will get maximum EMF of this cell as we calculated. Now let us see what is the effect of concentration on single electrode potential. So due to difference in concentration of the electrolyte into which the metal is dipped, the potential developed at the metal solution interface will be different. So let us see that. Now we are going to learn Nernst equation. It speaks the effect of concentration on the electrode potential. Means here, let us see, I have dipped a copper wire in a copper plus 2 solution. The concentration of copper plus 2 is 1 molar. In this copper plus 2 solution, we can expect a reversible reaction like this. Copper goes into solution, copper plus 2 deposits as copper. So this is what both oxidation and reduction simultaneously happening. So that develops some electrode potential here. Now the same copper rod I kept in copper plus 2 solution whose concentration is 0.1 molar. So from here the concentration has decreased. So once the concentration has decreased, here there are so many copper plus 2 and here are very less number of copper plus 2. So you can imagine what is the scope of the copper to go into solution. Is this copper easily going into solution? Definitely not, because of higher concentration of Cu plus 2, the ability of copper to go into copper plus 2 is less, means oxidation is prevented, means the potential to undergo oxidation is reduced. So, as concentration increases, as copper plus 2 concentration increases, oxidation potential of the electrode decreases. Oxidation potential of the electrode decreases, or otherwise you see here the copper plus 2 concentration is lesser than earlier. So, once there are few copper plus 2 concentrations, the ability of copper to go into solution is better, means here copper oxidation potential is somewhat better. So, lesser is the concentration, greater is the scope for the metal to undergo oxidation. So, as metal ions concentration increases, oxidation potential of the electrode decreases. In contrary, as the metal ions concentration increases, the reduction potential of the electrode increases. Reduction potential of the electrode increases. Let us see, I am taking zinc plus 2 in zinc. Again zinc plus 2 solution in zinc. Now, this is 0.1 molar and this is say 1 molar solution. Let us think about the deposition, that is the reduction. So, here zinc plus 2 want to undergo reduction to zinc. Here also same, but where the concentration is more, there the reduction ability is more, means zinc plus 2 more concentration is the case where the reduction potential of zinc is more, and here zinc plus 2 concentration is less. So, it cannot greatly undergo reduction. So, as concentration of the zinc plus 2 increases, reduction potential of zinc electrode also increases. As concentration of the zinc plus 2 increases, reduction potential of the every electrode increases. That effect of concentration on electrode potential is given by Nernst equation. So, this speaks, let us see, always we should use reduction reactions, always reduction. According to convention in electrochemistry, we should use always reduction potentials. So, electrode potential, that is reduction electrode potential, ERP is equal to E naught. E naught means standard reduction potential minus 2.303 RT by NF. N here is the number of electrons involved in the reduction reaction. So, in this reduction reaction we have 2 electrons. So, the 2 electrons should be kept here. And what is Q? It is nothing but equilibrium quotient. Equilibrium quotient, how do we write for this? Reversible reaction. As we know, equilibrium quotient is active mass of solid zinc by active mass of zinc plus 2 ions concentration. But for any solid, active mass is taken as 1 and the zinc plus 2 concentration, if the electrolyte is carrying 1 molar solution, we keep 1 here. If the electrolyte solution is having 0.1 molar, we keep 0.1 molar here. That is what ionic concentrations. Let us see how the electrode potential changes with the change in Q value or else concentration. Let us calculate the electrode potential of a copper electrode depending on concentration according to Nernst equation. So, calculate the reduction potential of copper electrode with copper dipped in 0.01 molar copper sulphate solution. So, the copper sulphate solution concentration is 0.01 molar. So, we are given that the standard reduction potential of copper electrode is plus 0.34 volts. So, according to Nernst equation, the reduction potential of any electrode is related to its standard reduction potential as E naught SRP minus 2.303 RT by NF into log Q to the base 10. So, here 2.303 R, T and F all are constants. You know R is 8.314 joules, T is absolute temperature, that is standard conditions or whatever the temperature mentioned, F is Faraday 96,500 coulombs. So, according to this electrode, the reaction is Cu plus 2 electrons gives rise to Cu. So, according to this reaction, the number of electrons involved is 2. So, we can substitute 2 here. And then, if you write the equilibrium quotient value for this, it is nothing but product concentration to reactants concentration. Concentration of copper metal by concentration of copper plus 2 ions. As the active mass of copper is 1, it is 1, and the copper plus 2 concentration was mentioned to be 0.01. This is the Q value. See, the Q value for this reversible reaction, if you write active mass of copper by active mass of copper plus 2. Active mass of copper we take as 1, and the active mass of copper plus 2 is nothing but concentration, which is nothing but 0.01. So, this is Q value, this is N value. Substituting in the Nernst equation, E reduction potential is equal to standard reduction potential value is mentioned, that is plus 0.34 volts minus of 2.303 RT by NF. Substituting all the constant values, it can reduce to 0.06 by N and then log Q. So, we will write log Q to the base 10, and we know N is equal to 2 according to the reaction, and Q is equal to 1 by 0.01. So, we write it as 0.34 minus 0.06 by 2 into log Q. Log Q is 1 by 0.01. So, this 0.01 is 10 power minus 2, coming to the numerator 10 power 2. So, this value will be log 10 power 2. So, minus 0.06 by 2, 0.34 will be as it is. And you know, log 10 square is nothing but 2 log 10. 2 log 10 is nothing but log 10 is 1. So, this whole value we can rewrite as 2 log 10, and as log 10 value is 1 and this 2 gets cancelled, this is 1 multiplied with 0.06. So, the overall value comes out to be 0.34 minus 0.06. So, from 0.34 we should subtract 0.06, and that value will be 0.28 volts. So, the reduction potential of this copper electrode will be 0.28 volts. So, this is how we can understand what is galvanic cell or voltaic cell, followed by the standard reduction potential values, electrochemical series, which is best anode, which is best cathode, and what is the maximum EMF you can generate from any two electrodes, and then how to calculate electrode potential if the electrode is not under standard conditions, like some else concentration of the electrolyte, like in 0.01 molar copper sulphate solution. When we keep copper rod, what is the reduction potential? That is based on Nernst equation we can calculate.